Okay, thank you everybody for coming to the quantum gravity seminar in Oxford. This week, we're very happy to have Antony tell us about an intrinsic cosmological observer. Go ahead.
Okay, yeah. Well, thanks a lot for the invitation, giving me the opportunity to talk about this recent paper that I put out. So I'll mostly be talking about this paper here, but there's also some things from a paper with Kristen Jensen and John Source from a few years ago that I'll be reviewing as well. Um, Okay, so yeah, the starting point of this is I've kind of for a long time been interested in entropy and quantum gravity, and there's one of the main differences I think between quantum field theory and quantum gravity is really how entropy behaves in the two situations. So in quantum field theory, if you're interested in talking about entanglement entropy, it has these universal UV divergences, and this is because quantum field theories have like a continuum description at arbitrarily short distance scales, and you have modes that are more and more entangled as you go to shorter distance scales, and so that leads to these UV divergences. On the other hand, in quantum gravity, the situation is a bit better. You generally talk about these generalized entropies where you can think of it as a quantum field theory entanglement entropy plus the area of the bounding entangling surface. And there's this old argument of Susskind-Uglum and many other papers that have verified this in different contexts is that this generalized entropy is a UV finite quantity, even though the individual terms in this expression are UV divergent. So the basic argument is there's kind of an area law divergence in the entanglement entropy, but that appears in just the way as it would from like loop effects that renormalize Newton's constant. So the idea is that this sum is independent of some UV regulator. So the thing I'm going to be talking about today is a sort of interesting intermediate regime between these two, finite entropies and infinite entropies, and it's coming from some works that have focused on semiclassical gravity, where you're thinking about taking the g Newton to zero limit, and it's not quite the same result as you would get in ordinary quantum field theory. So, okay, because g Newton appears in the denominator in this formula, your entropies themselves, the bare entropies, would diverge. But there's this interesting limit where you can make sense of these changes in generalized entropies. Um, yeah, so I'll be explaining this intermediate regime for most of the talk here. So one of the ways people have understood this difference has been in terms of the algebras of observables that you would write down and which the entropy is sort of characterizing. So in quantum field theory, using this language of von Neumann algebras, there's a very specific entanglement structure in quantum field theory that leads to what's known as a type 3-1 von Neumann algebra. And basically this type is related to some universal property. So it's related to the fact that you have local Lorentz symmetry in the theory, and you have a continuum description at arbitrarily short distance scales. And so you can use that to argue for the kinds of algebras that should show up for local subregions. So this semi-classical limit that I described before, people have understood it in terms of the algebra by saying that you get these type 2 algebras as opposed to this type 3. So for the purpose of this talk, the important difference between type 2 and type 3 algebras is this idea of semi-finiteness, or you can just think of it as that this algebra has a well-defined trace defined on it. And so a trace is just some linear functional that has this cyclic property when you stick operators in it. So it's a linear functional in which operators commute in expectation value. And so type 2 algebras have these things, and type 3 algebras, you can't really write down a tracial state like this. So the significance of having a trace on an algebra is that once you have that, given any state, which is in this case just something that computes expectation values, you can always associate a density matrix, which is just the operator you would insert into the trace that reproduces the expectation values of this state omega here. And so once you have a trace in a density matrix, you can write down this formula for the entropy that is minus trace rho log rho. And this is something that you can call the entropy. So in the type 2 case, you have to think a little bit about the interpretation because this trace is not the usual Hilbert space trace. It's something a bit more like an infinitely rescaled version of the Hilbert space trace. And so that normalization that comes into this trace means that you're thinking of an entropy minus kind of a background value. So you should think of this entropy here as a vacuum subtracted entropy. And the interesting thing is when you do this construction in gravity where you can identify these algebras, you can actually do computations where you compute this change in entropy and you can match it fairly precisely to changes in generalized entropy. So this entropy really is um, matching on to this area plus entanglement entropy that was shown in the previous slide. So one of the nicest examples where this came up was this work by CLPW, Chandrasekaran, Longo, Pennington, and Witten. And they were interested in writing down an algebra in the semiclassical limit in the static patch of de Sitter space.
Sorry, Anthony, can I just stop
Yeah.
you for a moment? In the
Sure.
previous slide, you said it matched to delta S rather than S gen. So I'm just trying to
Yes.
understand, does that mean you're not matching it's just a pure area term of the generalized entropy?
Right. Yeah. So
Does
you
that
have
match?
to you have to compute this area. You compute the change in the area at order G Newton, which you can do in this. And so this term has a finite fluctuation in this limit. And that's the thing you're matching. So the
And for the
reason you
type
get
2,
difference, just to say, the reason you get difference is related to this normalization that I was mentioning. For a lot of the algebras, that normalization is kind of arbitrary. And so it's sort of you relate it to the putative, background value of the entropy, which is kind of UV divergent, but the algebra is not really sensitive to it.
I see, but if I wanted, so I thought maybe in JT or something, you could really get the full entropy. The reason I'm asking is because, for example, the Strominger-Vafa computation, the reason it was
Mhm.
very impressive was you get the whole area term
Yes, yeah.
in a purely quantum mechanical way. And it seems like to understand a lot of the semi-classical gravity results and why it probes the UV kind of density of states, you do want the entire area over 4G Newton to come from a
Yeah, so I think that
big
again,
quantum number.
so the reason, just to clarify, we are focusing on this sort of intermediate regime. So I would say the Strominger-Vafa would be closer to this, where you have finite G Newton, you can just compute this. And so I'm emphasizing that this is a regime where we've taken G Newton to zero. So
Okay.
there's a version of their computation where G Newton goes to zero. I'm sure the entropy that they would compute blows up as well. And
I
so
see. Okay.
we're exploring
I,
this regime here.
I have a question related to what Gabriel's asked. Is it also true? I've heard that statement so many times that these algebraic methods are not capable of getting the tree-level entropy on its own. Like, these need something else, right? You can only get
Their area
differences or
term?
something. Yes, but on its own.
Yeah, I mean, usually what people say is like if entropies are finite, you're probably like actual, not these renormalized entropies, but if the entropy is finite, that really only happens with these type 1 algebras, and that's usually
Yeah.
including various non-perturbative effects that would
Right.
lead to such a thing. So yeah, I won't have really much more to say about it. It's very intriguing that, path integral methods seem to get this, like this finite thing by itself. But that's not a Hilbert space construction, but it's a thing that computes the answer. So it's interesting. Yeah. So there might be other regimes where you could say more, but yeah, I don't have anything specific to say about that at the moment.
Thanks.
Yeah. Okay, yeah, so I was describing this algebra for the static patch of de Sitter. So what they were doing is they were, again, analyzing this G Newton to zero limit. The algebra you write down is for the static patch are just the quantum fields that live in the static patch that they've shaded in blue here. But the additional difference from just ordinary quantum field theory is they want to gauge the time translation symmetry. So that's this boost symmetry that evolves you forward in time in the static patch and backwards in time here. And so they ran into an issue, which in ordinary quantum field theories, there's no operators that are localized to the patch and are also invariant under this boost flow. So sometimes they say that time translation acts ergodically. This is similar like in the Rindler wedge. You'll never have operators localized in the Rindler wedge that are invariant under the boost. So this was the original mode. So, okay, if your algebra, there's one operator that's invariant under the boost, it's the identity. That's not a very interesting algebra. And this is what motivated them to introduce an observer into the static patch of de Sitter. So they said, okay, if you want a non-trivial algebra, you kind of need a clock with which you can measure operators relative to. And so they introduced this model where you have an observer, they have a Hamiltonian, they perturbatively backreact on the geometry. And once you introduce this additional observer, you can explicitly write down operators that are invariant under the boost that simultaneously evolves the observer forward in time and the quantum fields in time. And roughly, there's a kind of, the operators looked like they're dressed relative to the observer's clock. And so in this case, there's a very specific type of algebra that comes up that's 2-1. These are interesting because they have a maximal entropy state. And so that's a concept that showed up in the de Sitter static patch in other contexts as well. So kind of arguments using the generalized second law. And so again, yeah.
Sorry, just to interrupt one moment. So just to remind me, you're gauging time translation because it's an isometry. And
yeah, so in this case, yeah, I would say in gravity, in some sense, you expect all diffeos to be gauged. So I'm going to describe some constructions where it's not really an isometry, and there's some arguments for that. But in general, the strongest argument is that you have this isometry, and it comes from these kind of linearization instabilities where if you have to lift it to the interacting theory, you get additional constraints basically at interacting order.
I see, but is that the only isometry in the game? Or, I mean, that preserves
the static patch in de Sitter has, rotations as well. There's an argument for why we don't talk about those. It's sort of, they won't have this effect where they change the type of the algebra. I think in principle, you're supposed to, have a frame as well and write down operators that are dressed relative to an observer's frame. They just don't have a big effect in terms of this like type 3 to type 2 and having finite entropies. So that's why you don't talk about the other ones. You're supposed to, but it's not a big well, there might be something interesting, but yeah, this finite entropy difference is not going to come from that.
I see. Okay, thank you.
Yeah, so in this case, they had this type 2-1 algebra, this maximal entropy state. So on the one hand, that was very interesting. There was a lot of both that you can match the generalized entropy, and then you have these features expected from kind of entropic arguments, like a maximal entropy for the static patch. On the other hand, it feels a bit awkward because you would expect there are really observers in gravity, but it feels like very crude to just write down this is, this operator that's stuck on a world line and it's only characterized by this Hamiltonian. And it's completely unrelated to the quantum fields. And so the CLPW construction, they did it kind of out of necessity. They needed a clock to measure positions of operators relative to. And so the idea is that once you introduce the observer, you have a new constraint and you can find things that commute with that gauge constraint. But yeah, it does feel a bit awkward. So there was a later development, which was this
Small
paper.
question. Sorry.
Yeah.
So you could have also introduced, so there's also this time translation isometry in Minkowski space. You could have done that. You could have introduced an observer there too. Can we learn anything new from there or no?
You mean like global Minkowski? So you're everything in Minkowski.
But I mean, over there you don't need to because whatever operator they're invariant under this like local operator. I mean, here you had an argument why you needed those, why you needed to introduce
in that
them.
case,
There you don't need to.
I think there are operators that should be.
Yeah, so there are, but if you introduce an observer there too, which in principle we could, right?
Yeah. So yeah.
But I mean, there's nothing to learn. There's actually something you're saying that's actually.
Yeah, in that case, it would be, I think you would expect these algebras to be a bit different. You would have these like type 1 algebras, so you have actual pure states and things like that, just because there's not a real horizon for the observer in Minkowski space. So yeah, again, some of the entropy questions are less interesting there. But I guess in principle, I can mention this Witten background independent algebra, which is very focused on the world line. And one of the ideas is that you can embed that world line in any background. And so depending on the background, he was saying you would get different kinds of algebras, presumably. So yeah, it's something you would do, but yeah, some of these entropy things would be less interesting there.
I see. Questions about, okay. Okay, thanks.
But this sort of algebra independent construction or background independent, these are not algebras or even von Neumann algebras, right? Correct? Is that right? That's
yeah. I don't fully understand the object. It is, but I think it was clarified. I asked Edward about it, and he did clarify it's not exactly an algebra, even though you call it one. Yeah, it's these like OPE algebra, but they're something else. Yeah, okay. So yeah, you shouldn't think of it as an algebra
because there's no Hilbert space to begin with, like in the sitter, for example.
Yeah, certainly there's no, and really it's not something that has the structure of an algebra. You don't have like things that you can multiply. Like OPEs are not actually multiplying operators because you have the little tilde, right?
The little tilde, exactly.
Yeah. So it's just a different structure. And yeah. Okay. So yeah, I kind of liked this work by Chen and Penington, who said, well, the only reason you introduced the observer was you needed a clock. And in inflationary examples, you do have a natural clock because you have some rolling scalar field, and that scalar field provides a clock. So this is a common thing in cosmology. And so they wrote down a fairly simple model of this, and they said, well, they didn't even have to introduce this observer. They could find operators that commute with this boost flow in that context. And you get a non-trivial algebra and can, again, do this matching of entropy. And so that's kind of nice because then now, okay, there's no observer really in that story. But so it does raise a few questions that I was interested in. And in particular is like, is there something that was playing the role of this observer Hamiltonian from the other construction? And that would be kind of interesting because then this would be a model where you really constructed this observer out of the quantum fields just because those are the only degrees of freedom in the model to begin with. And so this is the thing I wanted to explore in this work, is how you can think of their construction as an observer and a thing that it's observing, but all intrinsically to a quantum field setup. So the things I want to go over is, before I discuss this inflationary model, I wanted to give a few more ideas or intuitions for why these type 2 algebras are coming out. And I think an interesting way to think about what's going on, like why you're getting these traces, is coming from doing a procedure where you're gauging modular flow. And so I want to explain what that means and then argue that that's why you're getting traces. And it should be, I think, fairly intuitive why that procedure gives you a trace on the algebra. So after I do that, I want to apply this interpretation to this Chen and Penington inflationary model. And so there's an interesting way in which you find operators that commute with a modular flow, in this case, using a time averaging procedure. And that the fact that that's how they got the algebra allows you to use some math results to say, okay, this algebra has some specific additional structures, one of which is the existence of these observer operators. And so in order to show that you have an observer, you want to write this algebra via a procedure known as a cross product, which is essentially, I'll argue, is a way to decompose the algebra into an observer and the things that it's observing. And so this is how you would single out this intrinsic observer. Okay, so that's where we'll hopefully get to during the talk. We'll see. So the first part is just to explain why we're getting traces. And so the basic argument for why you get a trace is that first you argue that the transformation that looks like a boost at the entangling surface should be gauged in semiclassical gravity, just because it's a diffeomorphism. And then the second step is that those transformations also, you argue, generate a modular flow on the algebra of operators localized in a subregion. And we have some evidence for that. And in certain situations, you can actually prove this is true. So these 2 points mean that you should treat the modular flow on a certain quantum field theory algebra as a gauge symmetry. And so you get the gravitational algebra basically by gauging modular flow. And so this procedure in the operator algebra community is known as finding a centralizer of a weight. And there's a reason that these things usually have a trace defined on it. So the centralizer are just all the operators that commute with modular flow. So just to explain this argument a bit more, the context is always semiclassical gravity, where you're taking a g Newton to 0 limit of a quantum gravity type of theory. So in general, you're going to almost be doing quantum field theory on curved spacetime. That's the basic behavior. So you can carve out subregions since, okay, in small g Newton, you don't have to worry so much about diff invariance. So you can just write down subregions and assign operators smeared to subregions in a given background spacetime. And these algebras that you associate, say like AQFT, which would be all the operators smeared in the blue regions, they generally form type 3-1 algebras of operators acting on a Hilbert space. So in general, you say, okay, the operators in the blue regions are some algebra. The operators that commute with that are in this red region. They're the ones that are space-like separated from that. So they commute just by microcausality. And so these both act on a Hilbert space, but you don't want to assume some sort of tensor factor structure. And that's related to this continuum description, this type 3 algebra. All of the states are a bit too entangled to actually tensor factorize the Hilbert space. And in principle, you also include free gravitons because you take this limit g Newton to 0. So in a way that you get the free spin 2 particles, but all the interactions are suppressed by g Newton. So that's the quantum field theory and curved spacetime description. The additional component that comes in with gravitational algebras is that you want to account for diffeomorphism constraints. And so we want the operators to be dressed appropriately to commute with generators of diffeomorphisms. So the diffeomorphism we focus on for the whole talk is this boost diffeomorphism. So as I was mentioning to Gabriel, in principle, you want to account for all of them, but there is an argument that the boost one is the only one that can change the type of the algebra. So we gave a version of this argument in this paper with Jensen and Raju. So the idea is we focus on the boost diffeomorphism. So I've drawn this as with some arrows here. It's the thing that evolves you forward in time in the patch and backwards in time in the complementary patch. And so this is just generated by a Hamiltonian, which is some stress tensor smeared on a Cauchy slice like this. This diffeomorphism is required to vanish at the entangling surface, and its derivative there is supposed to be proportional to the binormal. That's just the condition that this flow stays within the diamond, and so it's parallel to the light cones at the boundary of the diamond. So that is the flow we want to gauge. But the claim is that this actually generates a very specific kind of symmetry on the algebra of operators in the subregion, which is called a modular automorphism or a modular flow. So at this point, I'll tell you what that actually is. The idea is if you're given some global pure state on the algebra here, well, so this is like this algebra acts on a Hilbert space. Generic states are going to be entangled for the algebra. So you can write down these modular operators, which are morally like the density matrix for this state times the inverse density matrix for the complementary algebra. The reason there are quotation marks here is because these density matrices for type 3 algebras aren't really well defined. But this is kind of the easiest way to see what these operators are supposed to do. So there's a more mathy way of defining this that you don't have to use the quotation marks. So the modular Hamiltonian is the log of this modular operator. So it's equal to the minus the log of the density matrix plus the log of the density matrix for the complementary region. And roughly you should think of this thing itself, each individual turn's kind of UV divergent. but this difference cancels out kind of at the boundary of the entangling surface. So this combination is a UV finite quantity. So modular flow is just the flow generated by this modular operator. But if we use this fiction where we factorize it with the density matrices, the inverse density matrix doesn't do anything. So it's like you're just flowing with the density matrix itself. And this is an important flow. It maps the algebra into itself. And it's characterized by the fact that correlation functions for this flow satisfy a KMS condition. So that's just the statement that if you have a float operator AS times B, that correlation function is equal to the same thing as the switching the order of the operators and analytically continue the flow time to value of I. So it's just saying that correlation functions are always thermal with respect to the notion of time defined by modular flow. Okay, so this is what modular flow is. Why would that be related to the boost flow? And this basically comes from the Unruh effect. So the idea is like near an entangling surface, the entangling surface should locally look like Rindler space, and any state on this algebra should approach a local Minkowski vacuum near the entangling surface. So for actual Rindler space and the Minkowski vacuum, we know from either the Bisignano-Wickman theorem or the Unruh effect that the boost generator is the thing that defines the density matrix. And so this modular flow is the boost generator exactly in that case. And so this is what motivated the conjecture from this paper that just by choosing the boost generator to choosing this generator to locally generate a boost near an entangling surface, that ensures there exists some state where this is actually the modular Hamiltonian for that state. Essentially, you can write down a state that's thermal with respect to, the one-sided part of this. And so the precise relation is that the modular Hamiltonian should be beta times this boost generator, and you have this usual relation between the temperature here, the inverse temperature, and the surface gravity from the Unruh effect. And in particular, a non-trivial part of this conjecture, so this kappa was defined by this relation of what the derivative of your vector field looks like near the entangling surface. It requires that kappa is constant along the entangling surface. So that's a non-trivial part of that conjecture. Okay, so for general subregions, we think this conjecture is probably true. There might be some additional restrictions on it. For the subregions I'm going to be considering in this work, which is the de Sitter static patch, you can actually prove that there is a state where the boost generator is the modular flow. And so going forward, we'll take this as a working assumption and understand the consequences of it. So the main consequence is that we've said you want to gauge this boost flow and that the boost flow is a modular flow. And so putting those two together is that we want to look for operators for the gravitational algebra that commute with modular flow. So this is known as the centralizer of the state. And there's a very basic argument for why operators that live in the centralizer have a trace defined on them. If you just take the expectation value of operators where both A and B commute with this modular flow, the fact that they're commuting with modular flow is like they're commuting with the density matrix because that flow is generated by the density matrix. And so if you think of this as trace of rho AB, because A commutes with the density matrix and because this trace is cyclic, you see that this expectation value has this cyclic property here. So just taking the expectation value of this class of operators in that state defines a trace. And so this is a basic argument for what's going on in a lot of these constructions. You looked for operators that commute with modular flow, and that just immediately gives you an algebra with a trace. Just a couple of comments on this is that this argument also works in the type 3 case where I'm not allowed to write down something like this where I have a fictional density matrix and a trace. But okay, you can look up in your operator algebra books that this argument basically holds in that case as well. And somewhat importantly for this is it also works for things that are known as weights. So these are just unnormalized states that give you finite expectation values on a dense set of operators in your algebra. Um, if you're if you want a canonical example of what a weight is, just think of the ordinary trace on an infinite dimensional Hilbert space. There's a subset of operators that have finite trace. Those are the trace class operators, and that thing is, that defines a nice expectation value on enough operators. So similarly, a lot of the things we'll be working with are these kinds of unnormalized states, and we'll see that come up later in the talk. Okay, so this argument says that we have a renormalized trace, and these traces lead to density matrices, so you can again compute these entropies here. And so somewhat generically, centralizers for type 3 algebras tend to be type 2. So this is this renormalized trace on a type 2 algebra where this entropy again is interpreted as a vacuum subtracted entropy. So one example that was the first example in this subject that was explained by Witten was this cross product example. And so it's somewhat instructive to see how this works in that case. So this is like this CLPW construction where you just add the extra observer by hand. So how did that construction work? We had all of the operators A, Q, F, T, which are like the operators in the static patch. And then we tensor in an observer algebra. So this was just taken to be an energy and clock operator, and you just take them to be canonically conjugate. So this is just like the X and P commutation relation. This is just all of the operators on an infinite dimensional Hilbert space. So this is still this is still a type 3-1 factor. So in this case, you have little h is like the quantum field modular Hamiltonian, and then this epsilon is the observer's Hamiltonian, and t is the observer's clock. And you're looking for operators that commute with h plus epsilon, which is the overall boost flow here. So this operator here is actually the modular Hamiltonian of the following weight. You can take whatever your quantum field theory state is here and just tensor in this Boltzmann-like weight for the observer Hamiltonian. Now, since epsilon goes from -infinity to infinity, you can see that this isn't really normalized because you'll get a divergence from here. But as long as you write down operators that kind of damp out the contributions at negative values of epsilon, you'll get finite expectation values in this weight. Okay, so this is the modular Hamiltonian for that weight, and then so you can write down a bunch of operators that commute with that. Explicitly, they're given by this observer Hamiltonian itself, and these sort of dressed versions of the quantum field operators where they're flowed in modular time in a way that depends on the observer's clock t. And this algebra is known as the modular cross product, and so then you can write down a trace on it. One way to write this trace is by this formula where you take some expectation value in the vacuum state and some sort of 0 t eigenstate, and this defines a trace on this. So I mentioned this just, yeah, go ahead.
Sorry to interrupt. I think I'm not sure I understand the notation for curly A alpha. That bracket, what does that mean here?
Oh. This I'm saying it's the algebra generated by the operators here. So take products, arbitrary products and limits. I don't, yeah.
Okay. And
yeah,
those are the things that commute with phi.
These all commute with this operator here. So this is not too hard to show. It takes a couple steps in basic undergrad quantum mechanics to convince yourself that this commutes with this.
I see. And that algebra is what you call the centralizer of that weight phi. Is that right?
Yeah, because this is the modular Hamiltonian for this weight, it's by definition, this algebra is the centralizer. And it's just because this weight, because this is a modular Hamiltonian, you should immediately expect that this algebra has a trace defined on it because of this argument about centralizers having traces.
I see. And the thing about the energy and time conjugate pair, isn't there some weird pathology? Like we never see that in quantum mechanics, right?
Yeah, it's if you want positive energy, you're not allowed to do this. So this example, you let epsilon go from -infinity to infinity. What CLPW did was they had an extra step where they said, okay, after you do this, you impose a further constraint that epsilon's positive. So that constraint ends up commuting with this, so you can do it in steps, and that's what leads to this type 2-1 structure for them.
I see, okay.
I think you can also write down a weight immediately where you say epsilon, you kind of forget about this T operator and you just say, you know, there's a specific weight and the operators that commute with it are roughly this times that projection on, you sandwich everything in terms of the positive energy projection.
Okay, thank you.
Yeah. Okay, so the other reason for explaining this in a little bit of detail is one of the things we're going to do is show that this cosmological algebra is a cross product, and I just wanted you to see what it is to be familiar with what we're aiming at. Okay, so now I want to move into the part where I describe this cosmological construction where you don't introduce this extra observer to get an interesting algebra. Okay, so this paper by Chen and Penington, just to set up what exactly they were doing a scalar field in de Sitter space, and again wanted to take this g Newton to 0 limit to suppress back reaction. So if you're in 4D, you can take this limit in a way that the cosmological constant is constant as g Newton goes to 0. And in a slow roll model, you can check that you can do that in a way such that these slow roll parameters basically go to 0 in the limit as well. The specific potential you write down is in exactly linear one. So you have a cosmological constant and then a linear potential for the scalar field. So you can take a limit where you kind of freeze the geometry to be exactly de Sitter. You have a scalar field living in de Sitter, and it sees this exactly linear potential. And additionally, you have these free gravitons in this model. For this talk, I wanted to analyze an even simpler model where just because it has the same effect that we're going for, which is this existence of a trace. And the simplification is just to work in 2D de Sitter. And so we're going to, the gravity is, okay, the connection to gravity is a bit lost because, okay, you don't really have pure gravity in 2D, but we're going to just do this same thing where we want to do the scalar field in 2D de Sitter and impose this boost constraint and see that you get non-trivial operators here. And this simplifies it because now there's no gravitons and you also don't need the higher angular momentum modes of the scalar field. So there's some computations that are a bit more explicit. Okay, so we're doing 2D de Sitter. Everything's nicest in conformal coordinates. So the 2D de Sitter metric is conformally flat in 2D. So the time coordinate here is this conformal time runs from -π/2 to π/2, and then chi is just a coordinate on the spatial circle. So these are the global coordinates in de Sitter. The static patch we'll take to go from chi between -π/2 and π/2 when t is 0. So the scalar field action is just the ordinary massless scalar field plus this linear potential here, which is just c times phi. And it's nice to write it out in these coordinates because it just emphasizes the fact that the scalar field almost feels like it's in flat space because 2D scalar is conformal, massless scalar. But this linear potential does see the de Sitter geometry here. So this model is very simple. It's free, and you can just quantize it in the dumbest possible way. You just impose some canonical commutation relations on a t equals 0 slice. And in addition to that, you need some sort of preferred vacuum state to define the Hilbert space of the theory. And so the vacuum state we want to work with is the natural de Sitter invariant state, which is this Bunch-Davies state. The way you would normally compute this, you do a Euclidean path integral over the sphere. It defines a wave function on the t equals 0 slice, and that wave function you can express in terms of the Fourier modes on the circle here. So if you do this computation, you see it depends exponentially on the 0 mode, the constant mode of the scalar field on the circle, and then it's quadratic on the higher Fourier modes. So these terms are kind of a normalizable wave function for the theory, but this is the funny one, which it's depending exponentially on the 0 mode, and the 0 mode goes from -infinity to infinity. So this wave function is very nice. It's de Sitter invariant here, which comes from the construction. On the other hand, it's non-normalizable because of this zero mode. And this is, so it has this exponential dependence on the zero mode because of our funny linear potential. So the scalar field was unbounded below. But this would show up, this problem would show up even if you did an ordinary potential. This is just that massless scalars in de Sitter space have certain IR divergences related to the zero mode. If we didn't have that linear potential, it would just be constant here, and a constant wave function is still not normalizable. So this is one of the places where we just have to say, okay, we have to interpret this as a wave. We don't try to normalize this, but as long as I give a wave function for some operator that suppresses the at phi 0 goes to minus infinity, so it kind of cuts things off there. This will compute expectation values for you. And this wave function, once you've given a wave function for the zero mode, it satisfies this Hadamard condition. So it's kind of unique in having the right short distance behavior for correlation functions. Finally, because basically as a consequence of doing this Euclidean path integral, it's almost immediate that this satisfies a KMS condition with respect to the static patch boost. And so you can argue pretty easily that the correlation functions in this Bunch-Davies wave function satisfy a KMS condition where switch the orders and it's thermal in this imaginary time here. So what that means is that this Bunch-Davies weight has a modular Hamiltonian that's just the static patch time translation generator. And so the operators we're looking for in the gravitational algebras are those that commute with this. And so in this case, we again are in the centralizer of this Bunch-Davies wave function. And so that's why we should expect the associated algebra to have a trace defined on it. So the thing that's different from the ordinary scalar field in de Sitter with no potential is that in this case we expect there to be operators that commute with this HC. So one way you can argue for it is to do this time averaging procedure. Say you wanted an operator that commutes with H. One way you can get that is just to average over all time translations of a given operator. So in the ordinary static patch of de Sitter, you expect this integral just to blow up on everything. The intuition is that, the static patch at late time equilibrates. And so, things kind of settle down and then you're just integrating over something that's not changing at all. But in this case, we have this scalar field that wants to constantly roll down to lower values due to this linear potential. And so if you give certain wave functions, certain dependence on the zero mode, there'll be operators for which this integral does converge. And yeah, things are time reflection symmetric. So, as you go to the future and the past, the scalar field is rolling down on a given solution. And so you can construct enough operators where this integral converges. And so that's the main thing, is that you expect a dense set of operators to have this integral converge, and then this just gives you a way of writing down non-trivial operators in this centralizer. So at this point, once you've argued that integral converges on enough operators, there's some nice math results that you can apply to characterize the associated algebra. So this is this work by Connes and Takesaki. They call this the flow of weights. So one of the things they explain is when you do this time averaging over modular flow, it defines a procedure that's known as an operator valued weight. This is just a procedure that's similar to taking a partial trace over part of a Hilbert space, but it's sort of a well-defined operator algebra construction. So second, this Bunch-Davies weight that we computed, whose modular flow we were finding the centralizer of, is almost defines a trace on this centralizer. So you say this Bunch-Davies weight, it's equal to, if you want to compute it on an operator, you can first do the time translation and then you can evaluate some other functional on that. And yeah, so this operator then is defined on the centralizer, so it will automatically be tracial because operators that you're evaluating this on are all fixed by the modular flow here. So what this shows is that this Bunch-Davies weight actually diverges on all elements of the centralizer because if this operator was already time translation invariant, this integral is just going to be integral of a constant from -infinity to infinity. But basically by writing it like this, where you first do this time translation and then you get a second operator, this sort of strips off that trivial divergence coming from the integral over time. And so that's this tau then is the finite piece that's left over, and that's this renormalized trace. And so the other thing you can use this math result is they gave a classification for when this integral on a type 3-1 algebra converges, and the kinds of weights where it converges are characterized by this single number, which is you just evaluate this trace function on the identity. And if it's less than infinity, you get this type 2-1 factor. So an example of this was this positive energy observer of the CLPW paper. And when it's equal to infinity, you call it dominant. It's a type 2 infinity factor, meaning there's no maximal entropy state. And this is the kind of thing that showed up in the cross product construction. So this observer construction before you did the positive energy projection. So in the context of the
Anthony,
scalar,
before you go on, just make sure I don't get lost. Can you go back one slide? First of all, when you say that T is like a partial trace, what are you partially tracing over?
It's kind of like the operators that are not invariant under the flow. The thing is, when you have a partial trace, you have like a collection of operators. You like have a tensor factorization of your Hilbert space. So you have operators here, and you have a second factor here, and you can trace out all the operators in the second factor. In this case, and so all of the operators in the factor you're tracing over commute with the things that you were writing down. The reason it's not exactly equal to a partial trace is that there's not actually operators that commute with this centralizer. So you can have these things where you have a big algebra and a smaller algebra, but there's not anything exactly in between in the sense that operators that commute with the smaller algebra. So that's the place where it breaks down. But roughly, you're getting rid of all of the operators that translate under this time translation thing. So that have non-trivial charge under the time translation.
I see. So that's the gauging you're referring to earlier.
Yeah. So you're going to the neutral sector of this time translation, and you're kind of averaging
and
over.
I didn't quite understand the stripping of, so you put this omega Bunch-Davies, you said it's composing a trace with this curly T.
Yes. So in principle, you can compute this Bunch-Davies weight by first time averaging and then computing this other renormalized trace on it.
Okay.
Yeah.
Okay. All right,
I was just writing this to say that there's kind of a you say you would want to take expectation values in the Bunch-Davies weight.
Yeah.
But those are all divergent because of this thing. So it's because for the operators invariant under modular flow, it diverges, but it diverges in a kind of universal way. And once you strip off that divergence, you get this finite piece left over, which is this trace.
I see. Okay. All right. Thank you.
Okay, so at this point, you can ask which kind of algebra does this cosmological example fall into? And there's a quick argument that you have to be in this type 2 infinity case, and it's because you have a symmetry around. So this massless scalar has a shift symmetry where you just shift the zero mode by a constant. When you do that, this Bunch-Davies weight just rescales, which you can see, right? If you shift the zero mode by a constant, that'll just be an overall rescaling of this wave function. And this symmetry also commutes with this boost flow. So it descends to a symmetry of the centralizer that we were talking about. So that's a symmetry of our gravitational algebra. And because it commutes with the H, but it rescales the Bunch-Davies weight, it must also be rescaling this trace that we found here. And so we have a symmetry of the algebra that rescales the trace. And this is only possible if you have a type 2 infinity algebra. Because, for example, so in a type 2(1) algebra, all operators have finite trace, including the identity. And you can't have a symmetry that rescales the identity. So it requires that there's some operators where this blows up on, and those are the things that rescale. Okay, so that says this weight is the same kind of weight that shows up in the cross product. And so now you can ask, how do you actually realize this gravitational algebra that we got by implicitly averaging over time translations? How do you realize that as an actual cross product? And so in this, so we want to find this operator epsilon that functions as the observer Hamiltonian. So in this case, this trace scaling automorphism, again, is important. So this, again, was the symmetry where you shift the zero mode of the scalar field by a constant. So trace scaling automorphisms are highly constrained for these type 2 infinity factors. And one of the things you know is that there has to be a fixed point algebra that is a type 3(1) factor. So these are, again, the types of factors that show up in subregions in quantum field theory. And this is a little surprising if you're familiar at all about how modular flow works, because on modular flows, depending on the state that you're working with, you can have operators that are invariant under the flow or not. So they can have these non-trivial centralizers depending on which state you're working with. So just to mention, if you like cohomology type things, there's an interesting relation to the cohomology of these Connes cocycles that's showing up here. So the fact that the modular flows can have different kinds of centralizers means that there's non-trivial cocycles in the operators that relate the flows, and in the trace scaling flows, that you can understand this fact that there's always a fixed point algebra, is that saying that it has a trivial cohomology. Okay, so what do we do with this information? The idea is we want to use the fixed point algebra for this shift flow as the quantum field theory algebra, and then we have to find another operator to add to it to generate the full gravitational algebra. Okay, so again, how would you find operators invariant under the shift? You can again do one of these averaging procedures where you just average over all of the shifts in time. So this again defines one of these operator valued weights. And so then the way we define the observer Hamiltonian is as an eigenoperator for this shift symmetry. So we want it to be a thing that shifts, that's not invariant under the shift symmetry. So how can you get that? You can basically, the way you construct such operators is you first start with some state or weight on the shift symmetric algebra. If you compose it with this averaging procedure that goes from the gravitational algebra down to the shift symmetric one, that will define a weight now on the full gravitational algebra. Once you have a weight, we know since there's a trace there, you can find a density matrix for it. And this weight here is invariant under the shift, whereas the trace rescales under the shift. And you can use that to argue that the density matrix for this specific weight rescales as well. So if you write the observer Hamiltonian as log of this density matrix, it'll be the operator we're looking for that shifts under this symmetry. So this observer Hamiltonian we've now identified, it generates actually the modular flow on the quantum field theory subalgebra, the shift symmetric algebra here, and it's an eigenoperator for this shifts flow. So this looks like all that you need to actually write it as a cross product. And so there's a theorem in the operator algebra language again that says these conditions are enough to prove that this is a cross product. So it's a cross product of this shift symmetric algebra by a modular flow that this epsilon is generating. So one interesting aspect of this is that there's a sort of frame dependence to this representation as a cross product. So in order to find this epsilon operator, we had to pick a state on the shift symmetric algebra. And in general, we could have picked another state. And if you pick another state, these observer Hamiltonians will shift where this gamma is some operator in the shift symmetric algebra. So if I add a thing that's an eigenoperator, if epsilon under the shift transforms by a shift and we add something that's shift symmetric, it'll still have the same transformation property. So this is kind of interesting because it shows that you can pick different observers, and it's in some sense a way of giving different notions of time that you're measuring the quantum fields with respect to, because each observer has its own notion of clock. And so this is so these gammas are related to these Connes cocycles between the different weights, and this connects to this background independence that initially showed up in this Witten paper, the first paper he wrote on this subject. And so you see that this cocycle equivalent should instead be interpreted as a frame dependence here, as opposed to actual background independence. Okay, but what's the conclusion at the end here? Is that we went through a procedure to write it as a cross product, and what that does is gives you a way of decomposing the algebra into kind of the quantum fields that we're observing and an extra piece, which is the observer Hamiltonian epsilon. And that different choices of observers can be related to different ways of representing this as a cross product. Okay. I'm a little behind on time, right? So I had a few, I can maybe go through this part very quickly. So I gave an argument for how you would in principle construct this observer Hamiltonian epsilon. You can be a little more concrete about it, where you explicitly write down a procedure for perturbatively computing this observer Hamiltonian. So what you need to do is find an operator that commutes with the boost Hamiltonian, and it is canonically conjugate to the thing generating the shift symmetry. That's the statement that it's, it shifts under the shift symmetry. So you can do this perturbatively in a power series in 1 over the slope of the scalar field. So the boost generator looks like the standard massless boost generator. So it's quadratic in, say, the momentum and the fields. And then the potential contributes a term that's linear in the fields like this. And so the idea is because the thing linear in the field will take, a sequence, a product of operators, and it will kind of lower the number of operators there, just because something linear in the field will generally take its commutator with another field will give something proportional to identity. And so you can perturbatively solve a recursion relation where you write this as a sum of a bunch of operators suppressed by the slope here, and you can solve this equation that it commutes with the Hamiltonian, where you find the piece lower order in this series that is not commuting with the free field, the quadratic piece, and you cancel it with a term by finding a commutator with the linear piece. And so the idea is, in this way, you write down a series of operators where each term in the series is, it's more non-local. So it's a product of n plus 1. So the term epsilon n in this series will be a product of n plus 1 smeared field operators. And you can also satisfy this recursion relation while also satisfying the second condition. So just a few comments on this is that you can see from this, when you go through how this goes, you can see that the solution for how to satisfy these commutation relations is not unique, and the different solutions correspond to this ambiguity we had in choosing different observers. And as I mentioned, each term is more non-local than the previous term because each term in that series, it involves one more product of fields. On the other hand, those non-localities are suppressed by 1 over the slope. So when the scalar field has a very steep slope, you should think of that as defining a very good clock, and operators look more local. So the effect of commuting with the boost Hamiltonian is suppressed in that limit. Okay.
Antony, it's like, oh, I was going to say you should summarize, but I think you're there.
Yeah, I think I'll try to quickly wrap up here.
Yeah.
So just to review what we did, I wanted, on the one hand, relate these gravitational algebras and the existence of a trace to the procedure of gauging modular flow, and I gave a bit of an argument for why that's the case. And then we went through this slow roll inflation example where you use this slow roll inflaton to actually construct operators invariant under the boost and also find an observer that's intrinsically constructed from the quantum fields. And we did that by writing it as a cross product. And there were some interesting ways in which the choice of observer is related to a frame dependence of the construction. So just to mention, there's a few other things in the paper. There was some discussion of time operators that I didn't really have time to go over, but there's a few puzzles with the construction on how to interpret the actual time operator, analogous to the one in the cross product. There's also a comparison to how you can think of this original construction of CLPW of the observer and de Sitter in terms of this Connes-Takesaki classification, and there was that parameter nu, and the difference was that parameter is finite in the CLPW construction. And I maybe just mention a related work where that was similarly looking for observers in a sort of holographic setup where you have time band algebras and sort of heavy states and CFTs, and you can see an emergence of a time operator in those contexts and a associated observer. Maybe just to mention a few things that, one of the takeaways was that centralizers were quite important, and there are other ways you could think about centralizers in quantum field theory, and there might be interesting constructions in de Sitter static patch. It would be nice to understand, more systematically how corrections at higher order in G Newton come into this story. And yeah, I think I mentioned this background independent construction of Witten, which has some interesting features. It goes a bit beyond what I'm saying, where I was kind of focusing on one background, but it would be nice to connect some of these ideas there. So basically, for what backgrounds can you say that you actually have an observer in that construction? Okay, so yeah, I'll conclude there and take any more questions.
Okay, thank you very much for the very nice talk. Do we have any questions for Antony? There were already quite a few, I think. Yeah, okay, so can I ask a question that maybe I'm not sure that I totally grasp all the details of this, but a question I always have is that is the algebraic formulation necessary in this set? I mean, it seems like you're using a very particular machinery to separate the observer from the system that you call this cross product, right?
Yeah.
But could I have done this if I didn't know algebraic QFT?
I mean, I think so what would you do? You would say I would want operators that commute with modular flow. So we're not doing, right? Say that should be your motivation for doing this. So you could just write down, this and say, I want to do this to find the operators that commute with modular flow. And then you can say, yeah, I know how to argue that there's a bunch of operators that do this. And also you kind of know these path integral methods tend to give you an argument somewhat directly that you have a trace defined as well. So it's not super rigorous, but it's, good enough for a physicist to say like, yeah, this thing has a trace and it's somehow related to this KMS condition. So from there, yeah, I mean, whether or not the algebra is type 2 or not, it's like you have a trace, and in principle, if you were doing quantum field theory, you could compute density matrices from that. And so similarly, you could say, how would I write an observer? I gave kind of one definition for how to think about the observer was this decomposition in terms of a cross product. Certainly the pieces there are, I think, simple enough. You're looking for operators that are invariant under a shift symmetry, and then saying, what else do I need to add? So yeah, depending on what you want to do, but I think you could write down the formula for the trace and convince yourself that it exists without no operator algebra, I guess.
Right.
So some of the operator algebra stuff it sometimes focuses you on the questions to ask. So like, yeah, knowing why, well, say, for example, the fact that this is a factor, so there's no central operators, it's very easy from this classification result to see, but it's, yeah. So it's always depending on what you want to do, whether the operator algebra stuff helps you. But I usually say it's something to do with it's usually pretty powerful for quantum information type questions. So entropies or relative entropies, it gives you some tools for that.
Albert, did you have a question?
Yeah, can I ask a question? Yeah, hi. So can you summarize again the role played by the inflaton? I mean, why can I just use gravitons for all this construction?
Yeah, I didn't explain. I briefly mentioned this. I wanted to argue that actually the inflaton was the central player, and the gravitons you can include or not. They kind of So the gravitons don't have this kind of zero mode behavior when you compute like a bunch Davies wave function, I'm pretty sure. So and yeah, and they act a bit more like the scalar field without the linear potential. Although I think they don't even have an IR divergence in if you compute the 2-point function for a bunch Davies. But yeah, it's really I think conceptually you need some sort of spherically symmetric type mode that defines the clock, and that's what the scalar field does for you here. It was also important that it's rolling down, and it's not, it's not a flat potential for it. And so I focused only on scalars, and then if you add the gravitons, the story goes through. It doesn't affect this basic argument that, this integral converges on enough operators.
Sorry, so can I ask a naive question? So if you have so there's somehow something slightly different between the two stories where you have a localized observer and the static patch in the sitter, and then a rolling scalar field in the sitter. So they both set a time thing that you're saying, but the fact that one observer is localized and then the fact that the field is like everywhere fills the static. So I mean, is that captured somehow by
Yeah, so
yeah, by this algebra?
some of this was this discussion of where this time operator was. So one of the things about the observer on the world line is it's very explicit that the time operator like lives on the world line with the observer there. And here it's very implicit what the time operator actually is. It's sort of not explicit anywhere in this. So I have an observer Hamiltonian. The time operator might be like this zero mode of the momentum zero mode of the scalar field, but yeah, it's more delocalized. But one of the reasons it's not obvious that this should be a cross product and why you kind of have to go through this roundabout way is because you don't have this very explicit time operator there. So it's a bit non-trivial to see that it has this description.
I see what you're saying.
So
But at the same time, you should be able to produce, like for example, I mean, if we knew some UV complete theory, you should be able to actually produce a localized operator, and you should be able to find the time operator of the a localized observer, and you should be able to find the time operator of that localized observer too, no? Or no?
I mean, yeah, there should the
I mean,
way
by
I
choosing a
would think
different
of that
state,
is that there's certain states
yeah.
that when you take this limit, they act like there's a clump of matter. I think that's the way this background independent thing by Witten was described, is that there's a class of states that really do have this localized observer. And then, yeah, if it's sufficiently localized, it probably has a time operator or something like a time operator.
Yeah, so
yeah,
there's an
but this is, I mean,
localized-
one thing this is saying is that you don't need this very explicit localized clump of matter. This is an example where it's a bit more diffuse and you're still getting a non-trivial algebra.
Yes,
so
that's correct, but you needed a rolling scalar field. So if you had a
yeah. So it's not going to work just,
yeah.
it's still a special class of setups. yeah, you would need to be in a situation where you're very high up on a rolling potential, where you can effectively say it's rolling forever in the limit.
Right, right. Or I guess I'm saying that you could in principle have you could in principle, actually my other meeting just started, but yeah, but you could in principle have a non-rolling scalar field, like actual de Sitter with the quantum field theory on de Sitter, and
Yeah,
then
like a massive
you can
scalar or
produce
something. Yeah.
scalar, like you can produce a localized lump, like you're saying.
Yeah, so I think you'd have to make that lump heavy enough in the limit to
Yeah, exactly.
be non-trivial. Yeah.
Exactly. Yeah, I agree. I agree. You have to be able to yeah, you have to be able to produce something, but you're saying in the algebraic operator language, the two are not actually very distinct. So they look similar. They both look like factorized products of some gravitational algebra times some like time yeah time
Yeah, so I mean there was
time
this
operator
description.
times some
Yeah.
clock basically.
Yeah, it's not exactly a product, but it's sort of there's a decomposition at least.
Yeah,
Yeah.
yeah.
Mhm.
Yeah, I see.
Yeah.
Okay, yeah, thank you. So I do have to go, thank you. But yeah, thank you so much for the talk. And yeah.
Yeah, thanks for coming. Yeah.